everyone. I'm Jinyu, come from Huazhong University of Science and Technology. I will present this work in terms of the background and motivation, details of series, evaluation, and conclusion. First, let's start with the background and motivation. The widespread use of new technologies increases the workload diversity. Data centers are facing challenges in task scheduling and resource management. Previously, enterprises ensure the QoS with the dedicated cluster or resource reservation. But this makes data center experience workload imbalance and low resource utilization. To reduce costs, enterprises try to deploy multiple workloads in one cluster with the mixed workload deployment method. This method has been used by Alibaba, Bing, and Google. Batch jobs are usually deployed with latency-sensitive services. The different resource requirements make it possible to deploy mixed workloads. However, QoS differences make this method face some problems. Next, we need to explore the causes by understanding the details of workload processing. A job is usually handled by multiple tasks. The task is the basic unit that does the actual work. We split the task lifecycle into the scheduling stage and running stage. In the scheduling stage, when there are not enough allocable resources, a task continues queuing and waits for released resources. When multiple workloads share cluster resources, the cluster presents a few idle resources. However, there are still many surplus resources that have been allocated but not utilized. The swallowed task is a task that has many surplus resources. When there are many task requests, the allocable resource shortage occurs. And where there are dependencies between tasks, a task may process slowly due to interference or insufficient resources. It even blocks the progress of the other tasks that depend on it. Such a task is a straggler task. The Bing trace data shows that the completion time of straggler task can be 10 times that of general tasks. Therefore, it's challenging to guarantee the QoS of latency-sensitive services. The previous solutions preempt the resources of batch jobs to ensure the resource requirements of latency-sensitive tasks. However, these solutions directly preempt the resources from batch tasks without considering the surplus resources. This can lead to greater performance penalties for batch jobs. Many solutions eliminate structural tasks with task replicas, where the task replica requires to allocate all the resources of the structural task and starts running again. This method loses the task progress and increases the task's resource consumption. Therefore, we hope to ensure enough allocable resources for latency-sensitive tasks to avoid long scheduling latencies, minimize the performance impacts of stragglers, and minimize the performance losses to batch jobs. To achieve these goals, we need to identify stolen tasks and reclaim resources on demand, identify and eliminate straggler tasks, and reduce resource preemption for batch tasks. Thus, we present CERES. CERES can ensure the QoS of latency-sensitive service and reduce performance penalties for batch jobs. By using of surplus resources, CERES consists of application data store, adaptive policy builder, and node task manager. The application data store includes a task data collector and a time series database. It's responsible for collecting, processing, and storing task status data. The adaptive policy builder consists of a task filter and an adaptive policy generator. It can screen out swollen tasks and straggler tasks, then makes adaptive resource decisions. The node task manager executes the task resource adjustments and monitors the status of running tasks. First, let's focus on the task filter. For each task of a batch job, the filter gets the task resource limits and the maximum used resources and computes the maximum actually used resource utilization. Then determines whether the task is swollen or not by comparing the results with the target utilization. If the maximum actually used resource utilization is smaller, the task is judged to be swollen. For each task of a latency-sensitive service, the filter gets the data of the last 3 monitoring time points and computes the current previous task process speed. Then estimates the task completion time. If the task processing speed doesn't tend to increase, and the estimated task completion time can't meet the service level objectives, the task is judged to be a straggler. The adaptive policy generator can generate appropriate resource adjustment decisions according to task types and available resources. First, the generator gets idle resources and counts the total resource requirements of the latency-sensitive tasks and straggler tasks. If the idle resources can't meet the total requirements, the operation to prepare resources will be tracked. The operation consists of 2 steps. The first step is to reclaim the surplus resource from swollen tasks, and the second is to preempt the resources from batch tasks. Once the allocable resources meet the total requirements, the operation should be stopped. Then, if straggler tasks exist, their resources should be expended. If no operations of reclaiming or preempting resources occur, and preempted tasks exist, it's necessary to restore their resources and resume their processing. All these policies are executed by the adaptive policy executor. Another component of Node Task Manager is the Task Status Monitor. The monitor obtains the status of running tasks and reports the data to the application data store. We have implemented CERES based on Hadoop and evaluate CERES. In this slide, we show the details of our evaluation setups, such as contingent class, cluster configuration, evaluation metrics, baselines, and workloads. The results show that, compared with Big C, the average task scheduling latency has been reduced by about 17%.